All right, everybody can hear me? Well, let's take that as a yes. All right.
We can hear you.
All right. And interestingly enough, I was saying in my previous meeting this morning, so this is this gigantic 17-inch screen, super high-powered gaming laptop, and it does not have a webcam. I'm guessing it's because it has a 17-inch screen. Maybe that panel, since it's fairly rare for laptops to have that big of a screen, they're much smaller selection of those. Maybe that just, they can't embed a webcam in them or something. I mean, this
My
is a
gaming laptop has a webcam in it.
What's this?
My gaming laptop has a webcam.
Yeah, same with mine.
It says a Core i9 10th generation. It's a 3090 GPU. I mean, just completely bleeding, dripping, bleeding edge.
Holy cow. Oh my goodness.
No webcam.
You would think they would have a camera in a gaming laptop, but apparently they don't. Oh my goodness.
Well, it's the first laptop I've had that doesn't have a webcam.
Yeah.
In it.
Yeah, you're good.
And it's who makes this? It's a Republic of Gaming. Is that a ATI? Well, whatever. So anyways, we're going to make do, and just for Jason, let's see, I got to find the tab. We were already on this tab. Is this where I had the thing? Yeah, it is. We're going to write merge sort today in a web page. not just merge sort, Emily. We're going to do it in an untested web C++ compiler because I don't have Linux on this box.
I mean, you could have installed Visual Studio and
well, I could have done a lot of different things, but I was making coffee.
coffee is more important anyway. So
Actually, it's a really weird coffee too. It's like a Door County cherry coffee bean that my wife got me because I have to have decaf.
cherry flavored coffee.
What's up?
Cherry flavored coffee.
Well, it's the beans are actually roasted with that because my coffee maker does, like, it grinds whole beans. I have like a fancy schmancy thing. And now because of my blood pressure, I have to drink decaf coffee, which I don't care. I don't need the caffeine from it. I just happen to drink a lot of caffeine because I drink a lot of coffee. So my wife got me these whole beans from Meyer that are like Door County cherry. So it's actually pretty good. I'm on my 5th cup. So hopefully no caffeine, or caffeine free means mostly no caffeine.
So I have a question for you, Dr. Lebman.
Mm-hmm.
What if there was to be a coffee distribution of Linux? Would you get it?
A coffee distribution of Linux?
Yeah.
I'm almost positive there has been one, like some distribution of Linux named after coffee.
Okay.
But probably. I do have a problem with coffee.
Okay.
Yeah, Emily, I agree. Dark chocolate espresso is really good, but that's, I mean, do you drink it as a cup of coffee, or do you do it like as a shot of espresso? Because a shot of espresso or 2 shots of espresso or something like that that's much more of a a shot or a latte. So that's more of like a compressed, flavor experience as opposed to bulk drinking. I mean, I'll do lattes or a shot of something, whatever they put in front of me, but I just like coffee. So if I'm making it myself, I just make a gallon of coffee. Well, I make it 1 cup at a time. My machine grinds it, but bulk drink lattes. Well, then you're not drinking coffee. You're basically bulk drinking steamed milk, which is fine. I'm not saying that doesn't taste good. You're just not getting that much coffee in that. I mean, I'm a fan of a venti caramel upside down. What do I do? Venti caramel upside down macchiato. That's my order at Starbucks when I'm going foo-foo-y. Otherwise, I just say, give me a venti dark roast and let's go. Okay, let's get into merge sort for Jason here. All right, so let's get this open. Well, we're going to start off by giving ourselves a array of random integers. So we have something to sort. So let me, what was that random thing, C++, random int. So we need time.h and so I'll grab these 2 things. And then I actually have the thing open on another window. So I'm using this online GDB thingy. It says it's in beta, so that should be perfect. So, so we'll go ahead and give ourselves those couple things. We're just going to create an initial array and fill it up with some stuff. So let's actually, I'll give myself the array here. So we'll create an int array. Well, let's see, let's call it int AR. We'll put I don't know, maybe 25 things in there. So we'll have our int array. Then we want to go ahead and fill that int array up with some stuff. So we're going to do something 25 times in this case. And actually, if you want to keep this relatively interesting C++, we'll do a define array size to be 25 like that, so we can change it easily. So we'll make our array size this guy. I is less than array size. Remember, does this require a? We'll find out in a second. I plus plus. Let's just make sure this loop is going through the right number of times. And actually, let's do. So I don't have to do printfs here. IO stream. So is it going to be this? Oh, and Dell here. That's fine. Okay, so we're spinning through our entire count here. So we have our array size and stuff. So now we're going to go and generate a random number. So this one. So we have to initialize our random number generator. And then we can use rand to give us our value. All right, so then inside here, well, we'll do it. We'll write a function to display it so we can do it before and after. So we'll go ahead and say AR at bucket I is equal to rand. And let's maybe give ourselves a number between like, I don't know, 0 and 100, something like that. So we'll say mod 101. And then let's write ourselves a display function. So we'll say void display array. This guy will take an int pointer AR as a parameter. And we're actually, I'm going to jump ahead a little bit here, because as we write our merge sort, we'll review what merge sort's going to be like here in a few minutes. But when we write our merge sort, it's going to be helpful for us to maybe display portions of the array to prove to us which aspects of the array is the part we're currently interested in looking at. So we're going to have this guy take in a int begin and an int end. With the idea being that we want to display the contents of AR starting at bucket begin all the way up to and including bucket end. So initially we would look at it from bucket 0 to bucket 24 for the legal buckets. But later on, for example, if we only want to show half of the array, proving one of the recursive calls is only showing bucket 0 through 12, for example, we can use the same function for doing that. So we'll do a for int I is equal to 0, I is less, I'm sorry, I is equal to begin. I is less than or equal to end, I plus plus. And we'll do our, I assume I could use a using namespace, right? Using namespace, std. So now I should be able to do C out. Where does end L live? Isn't that in standard lib? Oh, no. It's in IO stream. So I would have needed to do std : end L. So this should work here. So we're going to do AR at bucket I end L like that, and that should show it. So after we fill our array up with our random numbers, we'll go ahead and call our display array, passing it AR, passing it 0, and passing it array size -1, which is the last legal bucket. And it should show the full contents of that guy. All right, so there's our random numbers for the entire contents. And if you just want to see that are display methods working, if I say only give me the first 6 values, in this case bucket 0 through bucket 5, including bucket 5, I'll get a much shorter list of elements here. Okay. All right, so all we've done at this point is we've generated a list of random numbers. Done that before, yada yada yada. So now we have something that's not sorted that we want to have sorted. And we want to accomplish this with a merge sort. So let's go back and let's review. Oh, it's the screen, right? That I have my, oh, got some chats. Well, what am I going to give for you for homework, Jason? If I do it as a linked list. Let's see, now we're getting crickets. but if we when we do that, I'll you can swap payloads. You don't have to do the surgery thing. All right. So what am I doing? I want to hide floating. Actually, I don't really want to hide that because there's been some chats, so I'll leave that up there. I just need to get to this guy. All right, so let's get to some level of, okay. So I'm going to add, we'll do it with just with some text here, so I don't have to move too many things around. Well, you know what? It's really not the best way of doing it. But we're still going to do it that way. So we're going to say 4, 2, 1, 6, 0, 3, something like that. All right. So we're going to say that's our original array, original collection of numbers. And this collection of numbers is not in order. Now, remember, the core concept of merge sort says a list is only trivially sorted if it is a one list. All right, so merge sort operates off of this truth that if you have a collection of exactly one item, it is sorted. You don't have to do anything special. It's already sorted if you have a collection of just one item. All right, so merge sort says that as long as you don't have a collection of just one item, you're going to divide your list into two pieces. A left half and a right half. And you're going to call merge sort on the left half and again on the right half. So this is a recursive call to merge sort. This is another recursive call to merge sort. Why is it? So this is kind of that challenge that Jason's been sharing his terrified nightmare stuff with us about. Is recursion is a scary thing if you try to think about it in terms of recursion. If you try to think about it rather in terms of what is the right tool to accomplish a job, and just let the recursive nature of a solution happen. Because recursion is when a function calls itself from within itself. And that concept gets can make your brain kind of get into a weird knot, right? Now, eventually you'll get good enough at this. And when you take the CSC300 class, which most of you are probably taking with me in the fall, that's the class where we write our own programming language. But more importantly than that, that just happens to be the outcome of it. We used a functional language called scheme in there that doesn't support loops. So we do everything recursively in there. And you will see how, I don't know, easy isn't the right term, but recursion really isn't substantially more complicated than iteration using a loop, because we're accomplishing loops in that language using recursion. But the idea is if I need to get to the next value, I need some way of doing that. I add 1 to something and I call the function that gets to the next value a second time. Same thing's true here. I have a list. This list has a beginning of 0 and an ending of what? 1, 2, 3, 4, 5, an ending of 5. Is 0 and 5 different values? They are. That means this is not a list containing only one element, which means that by definition, this guy is not trivially sorted. Now, by sheer luck, this could be sorted. A human being could glance at this and say, oh yeah, those numbers are in order. But merge sort doesn't work like that. Merge sort says, look, unless you can guarantee me that at a glance, this thing is sorted, I'm going to divide it up and keep working on it. Okay. So it says, since this is not a one list, divide it in half. And what's our ultimate goal here is we want to sort this guy. So what tool do we have that knows how to sort? We have merge sort. Okay. Even though I just called merge sort the first time here, I know this guy's not sorted, so I'm going to split my list in half. I'll call merge sort on this half. I'll call merge sort on this half. All right, so let's look at this guy. Is this guy a one list? He is not. So what do? I split him in half. I call merge sort on the first half. And I call merge sort on the second half. Is this guy a one list? It's not. So I split it in half. I call merge sort on the left. And I call merge sort on the right. Is this guy a one list? Yes, I finished my job. That guy is sorted. The small, tiny little portion of our list is sorted. Similarly, is this guy a one list? Yes, the small, tiny little portion of the list that this particular call to merge sort was in charge of is sorted. We didn't have to do anything special. All we did is we operated off this rule that a list is trivially sorted if it only has one element in it. All right. So this call to merge sort ends. This call to merge sort ends. We bounce back up to this level. All right. And now we have that second call to merge sort. Well, we actually have to do a merge step here, but we'll get to that as a secondary piece. These are just we're just doing the recursive calls first. All right. So 4, 2, 1 split in half. We had 4, 2, and we had 1. The 4, 2 split in half. We had a 4, we had a 2, then we bounce back up. So that finishes the call to our left-hand side from this guy. Our right-hand side is already a one list, so it finishes, which then says this guy's now done, even though we're not doing the sorting yet. We're just doing the dividing portion of this. So then we bounce back up, and now we can get to the original second merge sort call, because this guy blocked. This merge sort call was sitting there waiting for this entire left side to finish. All right, but finally we can get to the second half here. And we say, is 6003, is that a one list? It's not. So we divide it in half. We have 60. And we have 3. Is 60 the one list? It's not. So we have 6. And we have 0. Oop. This guy's a one list, so we're done. This guy's a one list, so we're done. Bounce back up here, we're done. We bounce back up here, we call the second call to merge sort. This guy's a one list, we're done. So we finish here, we bounce back up here, and now we're completely done. So if these were our numbers, our individual calls to merge sort are going to deal with the full list like this: 4, 2, 1, then 4, 2, then 4, then 1, then 2, then 6, 0, 3, then 6, 0, then 6, then 0, then 3. That's the order in which our merge sort calls got called. So one call to merge sort started this, which turned into 2 calls to merge sort, which turned into 2 calls to merge sort, which turned into 2 calls, which turned into no more calls here because it was already a one list, which turned into 2 calls, which turned into 2 calls. All right. So what we want to do initially is we want to prove that we're calling merge sort on the right portions of our list, making sure that we understand how we're cutting our list in half. All right, so I'm going to comment out some of our stuff for random number generation initially, and I'm going to hard code in this 421603 so we can compare our numbers exactly to that. 421603, right? So I'll change this guy to 6. That's how many things are in there. And then we'll go ahead and I'm just going to comment out my fill with random number stuff. And instead, we'll just set bucket 0 equal to I'm just going to steal my list here, 421603. So this will be a 4. Two, 1, 6, 0, 3. Oh, not true. And then this is a 2, a 1, a 6, a 0, a 3, and then we'll call our array, proving we filled it correctly. Let's just make sure we're at a good starting point, and we should get the entire 421603 displayed. All right, so now we'll be able to match up to our match up to what we had before in our slide. All right, so we want to write a function called merge sort here. So we're going to have void merge sort, and merge sort is going to take in an array. It's going to take in a begin. It's going to take in an end. All right, because when we call merge sort, we're calling it on the portion of the array that this particular call to merge sort is supposed to focus on. All right, so where this is going to start off here, I'll go and get rid of this. Actually, I could have just left that there and just changed display array to merge sort. So my initial call to merge sort will be a single call. Merge sort, passing it my array and passing it the entire binding of the array, starting from bucket 0 all the way up to and including the last legal bucket of array size -1. That's what I'm passing into merge sort here. All right, so remember, merge sort has only completed its task if the values that was passed into the portion of the array that it was given was the one list. So if it's the one list, that means that it is already trivially sorted. How do I ask the question, is this the one list? What do I write here to ask, is this the one list?
If begin equals end, then it's the one list, but you probably want it in a while loop.
Okay. And you said something about a while loop?
Yes, I don't know if that's correct though.
Okay, yeah, that was good. That's gonna, so right off the bat, you're thinking loops. We're gonna accomplish this with recursion. All right, so our question is, we only need to do anything in here if the list is bigger than a one list, right? That's a true statement. Merge sort's job. Let's put this before. The job of this function is to sort the list from begin to end. That's what merge sort is for. If we went to Home Depot and we grabbed merge sort off the shelf and we looked at, what purpose this is for, it would say you feed it a beginning, you feed it a list, a first, the beginning of the portion of the list you're interested in and the ending of the portion of the list you're interested in. Its job will be to sort that one section of the list. That's what this tool does. All right. So don't really think about it from a recursion perspective. Just think about it that I have a tool that I can pass a list to, and I can also pass the portion of the list I'm interested in, and it will sort that for me somehow. So we already know that a list is trivially sorted if it is the one list. All right, so any way you cut it, we can say, we can go ahead and do a display array, AR, begin, end, right here at the beginning, right? That is the portion of the array that this particular call to merge sort is looking at. All right, but we only need to actually do anything if the portion of the array we're looking at is not the one list. So as you said, if begin is not equal to end, if those guys are different values, we do not have a one list. So we need to divide our list in half and call merge sort on each half. Okay. So we're only in this if statement here if begin and end are different values. So if they're different values, we need to now determine how to split our list in half. If we're operating off of our original list here, like our 421603, and I'm going to go ahead and we'll just put the bucket numbers underneath this just for our visual. This is 0, 1, 2, 3, 4, 5. All right. So that's the original portion of the array. We want to split it into buckets 0, 1, 2. Oop, Andrew. And bucket 3, 4, 5. And I want to call merge sort on the same array, but only from bucket 0, 1, 2 for one call. And then I want to call it on the same array from bucket 3, 4, 5 for the other call. For begin 3, end is 5, begin 0, end is 2. So the question is if I know this guy is not the one list, which means begin is different than end, I need to come up with the beginning and ending of the left half. And I also need to come up with the beginning and ending of the right half. So the beginning of my left half here is going to be the same as the beginning of my original call, right? So begin 1 is the same as begin was that was passed into this guy. Similarly, end 2, the end of my second list, my second half, is the same as the end of the thing that was originally passed in here. So we have given to us the beginning of the first half and the ending of the second half. Those are two trivial things that were handed to us. So I'm going to need to set up 4 variables here. I need end, I need begin 1, I need end 1, I need begin 2, and I need end 2. We already know that begin 1 will be equal to begin, the same value that was passed in here. We know that end 2 will be equal to end, the same value that was passed in here. So the beginning of the first half will be the same as the beginning that was passed into this call to merge sort. And the ending of the second half will be the same as the end that was passed into this call to merge sort. All right. So what we need to figure out here is where is the center? How do we divide it in half? So we go back here, we see that the end of the first half is 2. And the beginning of the second half is 3, which is 1 greater than 2. So we can even go so far as to say in here that begin 2 is equal to end 1 plus 1. Begin 2, the second half starts 1 later than the ending of the first half. So the real magic here is calculating the math for this part right here. How do I know where the end of the first half is? Okay, so here is my original list. We've determined this is not a 1 list. I visually shown that the end of the first half is a 2. How did we calculate that? How did we calculate that the end of the first half is a 2? Where this 0 here is begin and this 5 here is end. How do we calculate end 1 is 2? Go ahead.
End minus begin divided by 2.
Okay.
Those two.
Yep. You said end minus begin. Is that what you said?
Yeah, end minus the original begin, so 5 minus 0 divided by 2.
Okay, so 5 minus 0 divided by 2 would give you a 2.5, which truncates to 2. Okay, fine. So let's then go over here to the second half. If I'm dealing with the 3, 4, 5 section here, 5 minus 3 is 2. 2 divided by 2 is 1. Is this guy right here the center of this list?
Sorry, begin plus end divided by 2.
Yeah, begin plus end divided by 2. Now, let's back up here for a second and say, typically, this is the trick. This is why I said this is the magic. Okay, the trick with merge sort is when you're only looking at the left half, the math seems simpler. But when you look at, I need a generic solution for determining middle, and I need to do it across the entire list, even on the right half, the math becomes a little bit more complicated. So we might be lulled in to say, well, isn't the center just end divided by 2? For this left half, that would work, wouldn't it? 5 divided by 2 gives you a 2.5, which truncates to 2. So that seems like it works fine. But that would then be figuring out the same middle for the second half, saying 5 divided by 2 gives you a 2, when the middle is actually, well, the middle of this guy is actually bucket 4 to get you this half. All right, so you can't just take end and divide it by 2 and expect that that's going to give you the middle of that portion of the list. You have to take into consideration both begin and end. So what we do is we take the end, we add to it the begin, and then we divide it by 2. So 5 plus 0 is 5 divided by 2 gives us 2. 5 plus 3 is 8 divided by 2 gives us 4. Make sense? So that gives us the middle of the portion of the list that we're dealing with. So end 1 is equal to begin plus end, or you can say end plus begin, doesn't matter, divided by 2. And we got to spell begin right. So the ending of the first half will be begin plus end divided by 2. And the beginning of the second half will be 1 past that. This is the hard part of merge sort, that math, to make sure that no soldier is left behind. All right, that's how we calculate the center of the list, leading from starting at begin and ending at end. All right, so now we have our begin and end for our 2 halves. So I'm going to call merge sort, passing it the same array, passing it begin 1, passing it end 1. And I'll make a second call to merge sort, passing it begin 2 and end 2. This is a call to merge sort for the first half. This is a call to merge sort for the second half. Now, if you're thinking about this recursively, again, this is scary. This is a recursive call. This is a second recursive call to the same function within itself. So if recursion is already scary when a function calls itself from within itself, okay, then a function that calls itself twice within itself is basically hell on wheels, right? Only if you think about this recursively. If instead you think about merge sort as a tool, what does this tool do? It sorts this list from this position in it to this position in it. If I am inside of merge sort here, where I'm sorting this list from this position to this position, and it's not a one list, I need to divide my list in half, and I need to then use my merge sort tool to sort the left half and to sort the right half. The fact that it happens to be accomplishing this through recursion is relatively insignificant. It has consequences in that it's memory inefficient. You know, it's using a bunch of stack space because it has to put the current version of merge sort completely on hold. So this first call, this original call to merge sort, has to wait until both of these calls return before it can do its merge step. All right. But in any case, if we try not to get sucked into this is recursion and instead just say, I need to sort the left half and I need to sort the right half, do I have a tool laying around that knows how to sort stuff between certain ranges? I do. It's called merge sort. All right, so what we want to see right now is we want to see that we're calling merge sort on the right portions of our list. We'll have our initial call here to merge sort, which will show the entire list. Then we'll see that begin and end are not the same. So what will we do? We'll divide it in half. We'll call merge sort on the left half. We'll call merge sort on the right half. The left half will get called first. We won't come to this line here until this call has completely ended, which means it's halved itself potentially multiple times. So our second call to merge sort is going to be on the left half here. So we're going to display just the stuff on the left half. And then we're going to see, oh, begin is still not equal to end. So we're going to divide the left half in half and then call merge sort on each half. So that's where we get back to this picture where we say, here's my original call, 421-603. I'll split it in half. I'll call merge sort on the left, call merge sort on the right. But this call over here on the right will not happen until all of this is finished, because this guy blocks. So the second call to merge sort is going to be on 421. The third call to merge sort will be on 42, then 4, then 2, then 1, then 603, then 60, then 6, then 3, then 0. That's the order for our calls following these recursive calls. And it's because this right half blocks until the left half is done. This right half blocks, well, this left half blocks the right half from starting until the left half is done. So when I call the merge sort of the left half here, this 42, and then I call merge sort of the right half, this 1, this call to merge sort will not happen until this whole left side is finished. That's how recursion works. So our hope here is that if we're calling merge sort the right way on the right halves, we will get displayed to us the portions of our array that we're supposed to be paying attention to in the right order. Let's go ahead and run this. What's the capital S? Call it right down here. Yep. Okay. merge sort port. Spelling. Merge sort. Oh, and my display, here, we'll make it look cleaner. This worked, but my display shows it not all on one line. So what I'm gonna do is I'll put a space after it here, and then I'll say C out and L. So that'll put it on one line, so we're able to see the portion a little bit, well, a lot bit cleaner. So there's our original top list. Here's the left half of that guy, the left half of that guy, the left half of that guy, the right half of that guy, the right half of this guy up here, the right half of the original guy, the left half of that guy, the left half of that guy, the right half of that guy, then the right half of this guy up here. So we had all our correct merge sort calls called on the portions of the array that it was supposed to get called on. We haven't done any sorting yet, but we've divided up our collections in the right order now, such that our merge sort calls go through, they're looking at the right sections of our array, and it's stopping at some point. We're not in some infinite merge sort loop. So we definitely stop when begin and end are the same, and that's when we hit our one list. So when we got down to like a 6 here, we didn't try to divide that up into 2 halves, because we only do something if begin and end are different. All right, so any questions about how we got to this particular point? Because at this point, we've covered the hard part of merge sort. The next part of merge sort just feels a little tedious, but it's just moving stuff around. But the part of merge sort that's intimidating is those 2 recursive calls. So do we have any questions about how these 2 recursive calls are working and how we're calculating the left and the right half of our list here before I keep trucking? Okay, so now we want to look at the merge step. So after, for instance, let's just look at the simple case down here. This will be an easy way for us to, I'll just separate this here. We'll just look at this piece right here. So we had our call to merge sort here on the 4 and the 2. We decided that is not the one list. So we'll call merge sort on the left half, and we'll call merge sort on the right half. The left half was a one list, so it's done. It's sorted. The right half is a one list, so it's done. It's sorted. So when we come back up to this level, this is after our second call to merge sort. So the first call was here, the second call was here, both of those guys returned. So now we're sitting at the line of code immediately following our second call to merge sort. That second call to merge sort, well, after that second call to merge sort, we're guaranteed one thing. We're guaranteed, and I'm going to put it in a comment in our code here. Now the left half is sorted and the right half is sorted. We need to merge them together into a single sorted portion of our list from begin to end. All right, this is where the merge step comes in. All right, so and we're going to write a function for this. So we're going to say void merge. We're going to give it the whole array. We're going to give it a begin 1 and end 1, a begin 2 and end 2. Those are the two halves of our array. The beginning and ending of the two halves that are sorted in and of themselves. We know that this array AR from begin 1 to end 1 is already in order. And we know that this array from begin 2 to end 2, that portion is already in order. Our goal here, the goal is to ensure that the array from begin 1 to end 2 is in order. So we merge them together. That's what we're accomplishing here. All right. So again, we'll look at our simple example here, then we'll go up to a little bit more complex one, but the algorithm is the same. All right. So we know that even though I'm looking at it as a single list, we really have two halves of our list here, right? And this guy is bucket 0. And this guy is bucket 1 from our original list. So begin 1 is 0, end 1 is 0, begin 2 is 1, end 2 is 1. So that's the dividing factor for the two halves of our list. We know that this first half is sorted, a 4 is already in order. We know the second half is sorted, 2 is already in order. What we want to do is we want to now overwrite this part of our array with these numbers in the correct order. Now, a human being can look at this and say, oh, okay, well, 4 is not less than 2. So really the correct order for this should be a 2 followed by a 4. That's the job the merge step does. So what the merge step does is it first creates a duplicate. Well, it creates an array that's big enough to hold the contents of the original one. And then what we do is we have a series of competitions. We're going to keep track of where we are in the first part of the list, and we're going to keep track of where we are in the second part of the list. So who wins the race? Who's the smaller value? A 4 or a 2? 2 wins the race, right? So we're going to go ahead and put in our little answer section here. Well, 2 as our initial winner. And then we're going to move our pointer over here, and it's going to run off the end of this right half. I no longer have participants to compare in the right half of my list. So now it's a one-man race. Who is the next value to go into our sorted list? Is it a 4 or is it an illegal position? 4 wins by default. So there's our 4. Then what we do is we copy those values back over to our original array. This was a temporary array. We copy those values back over our original array, putting our 2 here, our 4 here. Remember, this is happening inside of memory. So that means that change had side effects. So there's our 2 and our 4 there. There's our 2 and our 4 there. All right, so now this call from up here, the left half has now returned, and you see how the left half is now sorted in and of itself. The right half gets its second call. It's a 1 list, it bounces back up. So the left half 2 and 4 is sorted. The right half 1 is sorted. Now we perform that same merge step. We give ourselves an array that's big enough. And we empty this guy out because he's there to house our values. So who wins the race, a 2 or a 1? A 1. Who wins the race, a 2 or an illegal position? A 2. Who wins the race, a 4 or an illegal position? A 4. So then we copy the values back over here. So we have a 1, a 2, a 4. And again, we're making those changes in memory. So this is a 1, a 2, a 4. So now this call, this left call to merge sort has finished. And notice that the left half is now sorted. So we can make our right half call. Same stuff will happen, yada, yada, yada. All right, so this merge step only operates on the portion of our list where we're currently focusing. So we go into merge step here, and our job is to create an array big enough to hold all the values between begin 1 and end 2. Okay, begin 1 and end 2. So if begin 1 was 0 and end 1 was 0, begin 2 was 1 and end 2 was 1 by our first example. The way we get the size is by saying end 2 minus begin 1 plus 1. We can't just say N2 is the size because we might be dealing with the right half of the array somewhere where N2 is a 7. And we might only be dealing with 4 buckets or 2 buckets. But if we happen to be dealing with the right half of the array, N2 is going to be a larger value. So the size of our temp array, int temp, will be N2 minus begin 1 plus 1. That's the number of elements that we're going to need to store. All right. Now we even know how many winners we need to pick. Parent I is equal to 0. I is less than N2. Actually, I'm going to do. I'm going to say size is N2 minus begin 1 plus 1. So we'll make this guy size. That's the number of elements that are in that temp array. We'll say I is less than size, I plus plus. So I've kind of referenced these guys as races. We have like a number racing against another number, and we pick the smaller of the two. Think of that, the value is like time. We pick the smaller of the two as the winner. This is how many races are going to be won. So this is the number of winners that we need to declare. And we're going to store the winners inside of temp. And then we'll copy those values back into our array from bucket begin 1 to bucket end 2. All right. So first thing we do is we're interested, if we go back over here, when we have 2 legal positions. That is, if we want to think about begin 1 and begin 2 as being the current place on our 2 arrays, we could create another variable if we wanted to. So if we want to just keep these things completely separate and not break begin 1 and end, we could say int pause 1 is equal to begin 1. Int pause 2 is equal to begin 2. So now we have these 2 variables that keep track of where we currently are looking on the left half and on the right half. So pause 1 starts off at the beginning of the left half. Pause 2 starts off at the beginning of the right half. Now, how do we know if pause 1 still points to a legal place on the left half of our list? What question do we ask? How do we ask if pause 1 points to a legal place on the left half of the list? How do we ask that question?
If pause 1 is less than begin 2.
Yep, that'll work. If pause 1 is less than begin 2, or we could say if pause 1 is less than or equal to end 1. Okay, so that's good. So if pause 1 is less than begin 2, I'm actually going to write it as the end one version. But what you just said is equivalent to what I just wrote here. They both mean the same thing. And pos 2 is less than or equal to N2. If both of those things are true, pos 1 is less than or equal to N1, and pos 2 is less than or equal to N2, that means we have two legal runners in our race. So now we want to ask the question, who wins? Right? Because in this case, we don't have illegal positions. We don't have a single guy running the race. We have both of them legally running, and we have to actually pick a winner. So we'll say if AR at bucket pos 1 is less than AR at bucket pos 2. If AR at pos 1 is the actual winner, then we're going to say temp at bucket I will get AR at bucket pos 1. And we'll say pos 1 plus plus. Else, if the element at position pos 1 wasn't the winner, then the element at position pos 2 must have been the winner. So temp at bucket I gets the value of AR at bucket pos 2.
I have a quick question.
Yep.
Just to be clear, when you say it is the winner, that means it is smaller, correct?
Smaller.
All right, perfect.
But if we were doing merge sort in descending order, winner would mean the opposite, right? Right now we're writing a traditional sort that goes from smallest to largest. So the winner would be the one that is less than the other one. But if we were doing our sort, if we were changing our merge sort, and we'll do this at the end, we can just see it. But if we were changing our merge sort to be from the largest to the smallest, we would just ask this question backwards. We would say if AR at bucket pos 1 is greater than AR at bucket pos 2, then he's the winner, because we are more interested in larger values than smaller values. But because we're doing a traditional sort in ascending order, smallest first to largest later, we're interested in the smaller value. That makes sense?
Yes, thank you.
All right. So if both of these guys are legal positions, we're going to figure out who the winner is and then record that winner inside of our temp array and make sure we increment the position on whoever the winner was, so we don't have him run the race again. So that's what we do inside that first if. Now, if this first if here, this guy, is false, that means one of our guys, pos 1 or pos 2, is actually off the end of his list. And therefore, the other guy is the winner by default. So else if pos 1 is less than or equal to N1, that means pos 1 is still legal. I'll just write it. Then we'll say temp at bucket I is equal to AR at bucket pos 1. Pos 1 plus plus. Else temp at bucket I is equal to AR at pos 2. Pos 2 plus plus. If they're both legal, compare them. If only pos 1 is legal, declare him the winner and increment pos 1. Otherwise, pos 2 must have been the winner, so declare him the winner and increment pos 2. We don't need to find out if both of them are illegal because of the way we're running our loop here. We could have run our loop in a while loop and said, while pos 1 is less than or equal to N1, and pos 2 is less than, well, or pos 2 is less than or equal to N2, keep doing something. But we happen to know that we need to pick size number of winners. So this for loop that takes I on a journey from 0 to size, not including size, already will do this logic the correct number of times. It's equivalent to asking the question of doing a while loop, while pos 1 is less than or equal to N1, or pos 2 is less than or equal to N2. It'll run through the same number of times. All right. So after this for loop, temp is filled up with our values in the correct order. We need to now transfer those values back over to AR, overwriting the old contents of AR with the contents of temp between begin 1 and end 2. We know that temp is indexed from 0 to 1 to 2 all the way up to, but not including size. But the portion of AR that we're copying values back into might be buckets 6, 7, 8, something like that. So we know that we actually need to place stuff between begin 1 and end 2 inclusive. Those are the values we need to actually place. Now we can use the for loop to create multiple values, like it's technically legal to create more than one counter here in our for loop, but just so we don't confuse things, we'll say temp pos will start off at 0. And we'll go ahead and say AR at bucket I is equal to temp at bucket temp pos. And temp pos plus plus. So this will take us, this will copy temp at bucket 0 over AR at bucket I, where I started off at whatever begin 1 is. All right, so temp is always, since it was a temporary array that had 7 elements in it, for example, it will always be indexed from 0 to 6 in that case. Where if begin 1 to end 2 was still 7 values, nothing is preventing it from being like bucket 7 to bucket 13, for example. So we need to make sure we copy the values from the correct positions in temp and overwrite the correct positions in AR, which is a pointer up in memory. So this will copy those contents over. So after this is done, now AR is overwritten between begin 1 and end 2 with the values in order. And this call to merge and merge sort can end. All right, so that's what merge does. Now, one thing I want to point out here, though, is even though merge seems a little bit complex, it's a whole bunch of simple little questions, right? If both runners are legal, decide who's the winner. If only one of them is legal, declare that guy the winner by default. If the other guy is legal, declare him the winner by default. This isn't a hard collection of if statements here. It's an important collection of if statements, but I'll still go back to that saying that all hard programs are made up of a bunch of easy parts. All right, so now down here, if we know the left half is sorted and the right half is sorted, we just call merge, passing an array, passing it begin 1, end 1, begin 2, end 2, and have it do its thing. So now after we call merge sort on this, we can then do a display array AR from 0 to array size -1. And we should have it if we do that beforehand as well. Just proving it was out of order, then put back in order. We should have a working merge sort. There are too few arguments to display array. Oh, I missed a comma here. So there is our guy at first, 421603. And here he is after he sorted 012346. So there is working merge sort for an array of integers. I would probably come into merge sort here in reality and no longer display the contents of what each step was looking at. That way it just looked like it works. Shows you the before and after. Here's before, here's the after. And that guy has it all sorted. All right, so I'm going to copy that. And I'm going to go into 300. What code snippet? Where's my code snippet? I have to start with create a post. So,
Isn't code snippet under attachments?
well, this looked like it did it. Or at least close enough. There's your code. So there's a working merge sort. So your homework for Thursday create a linked list and fill it with random integers. You can even hard code it with the values from our example if you want. Write merge sort for the link for that linked list. I'll put a little comment. You may swap payloads instead of updating pointers. I'll just leave it at that. Submit a GitHub link and a self eval. All right. So questions about what I'm asking you to do?
Just to let you know, you didn't send the code in Slack yet.
Are you lying?
No?
Are you still lying? But like I didn't hit the send button?
Correct.
Yeah, there's no messages on Slack with the code.
Where's Slack live? Here's Slack lives. Oh, so I just put it in there. Oh, I gotta hit this one. How about now?
I think it's because it's not from the code block, so it's like thinks you're trying to do like the Slack command or something.
Okay. That. I thought this was a create text.
You try that. Yeah, that's it.
Did that do it?
Yes, it did.
All right. Now I'm going to go ahead and delete this just for Jason so he doesn't have access to it. All right. I'll see everybody on Thursday. Probably back in person. I'll have my laptop this afternoon.